Modern militaries rely upon aerial refueling for both military and humanitarian operations. However, there is currently no method for refueling unmanned aerial vehicles. With the ever-increasing dependence on these UAVs, refueling tankers will adapt to provide safe and effective refueling operations using automated aerial refueling. Previous efforts at AFID have shown that a real-time solution is capable of centimeter and sub-degree level accuracy when an unobstructed view of the receiver is available. However, the tanker's boom obstructs up to half of the receiver upon approach. This video will present a solution that mitigates the effects of the tanker's boom through shadow volumes. Our solution utilizes the following pipeline to estimate receiver pose. Our simulation updates the receiver position following a predefined flight path. We then capture the stereo imagery of the approaching receiver from our tanker-mounted vision system. We then utilize OpenCV's stereo block matching to generate a disparity map of the captured stereo imagery. A disparity map represents the distance between two corresponding points in the left and right images. Smaller pixel differences are seen in white, meaning that the object is closer to the camera. Larger pixel differences are seen in black, meaning that the object is further from the camera. Utilizing the disparity map and the reprojection matrix calculated during pre-processing, we can generate a three-dimensional point cloud. These three-dimensional points are seen as the yellow dots. Two forms of filtering are applied. We filter out points greater than 1,000 meters away, as well as apply OpenCV speckle filtering. The tanker's boom generates a large number of sensed points that we currently don't care about. To remove these points, we utilize ray plane intersection. We cast a ray through each point and determine if it collides with the boom. If the ray does, we remove it from the point cloud. The green dots seen here are points removed through this technique. We then register a reference model of the receiver, seen as the red point cloud, to the yellow sense point cloud through the iterative closest point algorithm. The position and orientation of the red reference point cloud is our estimated pose of the receiver. At close ranges, the tanker's boom occludes varying portions of the receiver aircraft. Thus, our red reference model must dynamically update to match what can be seen. We accomplish this through shadow volumes. A shadow volume is defined as the volume of space occluded from a particular light source by an object. If the eye point, or camera, is coincident with the light source, the shadow volume is the same volume of space that is blocked from view by the object. Here, we can see the shadow volume generated by the boom from the view of both cameras. As the receiver approaches, we update the red reference model by determining if any points are within the shadow volume. Here we can see the reference model within the shadow volume. Red points represent the points that can be seen from both cameras. Cyan represents what is only seen by the left camera. Green represents what is seen by neither camera, and blue represents what is only seen by the right camera. If a point of the reference model is within the shadow volume, we remove it from the reference point cloud. We then utilize this decimated reference model for our next iteration through the pipeline. Now that the pipeline is defined, let's see the computer vision pipeline in action.